In this video we will talk a little bit about the implementation of the p-median procedure for cellularization of machines in Excel. So why is this important? Let's say that you have a machine part incidence matrix as the one shown in this matrix. Essentially here the numbers 1 to 6 represents machines on a factory, and the numbers 1 to 8 represents part in the same factory. So this factory fabricates with 6 machines, 8 parts. Some parts visit some machines. Part 1 visit machine 1, 3, 4 and 6. Part 2 visit machine 2, 5 and 6, and so on. So it captures the visiting of parts on machines. So given this matrix, we want to create cells or groups of machines in order to have more control over the production. If we create the small cells inside the factory, it's like having small factories inside our big one. So it will be easier to control the production of this factory. So how do we join together machines? Essentially, the idea behind this method is that we join together machines that are similar. What is the concept of similar? Similar, we can say that two machines are similar not because of the process that they perform, but because of the parts that are visited. So you can see that machine 1 and 3 are very much similar because the same parts visit these two machines, except for 5. Maybe the rest parts visit both machines. So we could say that machine 1 and 3 is similar. Maybe we can find another machines that are not very similar. It looks like 1 and 5 are not very similar. So this concept of similar or dissimilar is going to be best understood if we essentially during this video accept that dissimilarity is going to be similar as distance. Then it's going to be easier to explain. So in the whole video, dissimilarity is going to be the same as distance. So we could say that if two parts are very dissimilar, it's kind of the same as saying that both of them are very distant one from the other. Just like here you have 6 machines. We could say that 6 and 5 are very similar, so they are close. Or maybe we could say that 1 and 4 are very dissimilar, so that's why they are very far away from each other. Okay. So if we want to create groups, we could say that these groups will be very well created if we join machines that are very close or similar. If we merge in the same group machines 6 and 5, is a good procedure because 6 and 5 are very similar or very close. Okay. How this procedure works? Essentially, in this procedure you choose 2 machines that are going to act as seed machines or seed points, and these seed machines or seed points are going to attract the other machines based on the criteria of what machine is closer. So let's say that machine 2 and 5 are the seed machines. That's why I have essentially marked machine 2 and 5 with this circle, red circle. So 2 and 5 are the seed machines or seed points. So machine 1 is going to be assigned to 2 because it's closer than machine 5. Machine 2 is going to be assigned to itself. Machine 3 again is going to be assigned to 2. Machine 4 is going to be assigned to 5. 6 to 5. Okay, then essentially your machines have traveled a distance. You can add the distance 1 to 2 plus 3 to 4 plus 4 to 5 plus 6 to 5, then you will have a number. But if you choose a different configuration of seed points, let's say that 1 and 3 are the seed machines this time. Okay, so that's why I have marked 1 and 3 with this circle. Then machine 2 is going to be assigned to 1, 5 to 1, 6 to 1, and 3 has been able to attract only 4. Then you have another solution and another distance. This time the distance is going to be distance 2 to 1, 6 to 1, sorry, 5 to 1, 6 to 1, and 4 to 3. That is going to be the full distance. So what is better, this or this? We can add the distance and choose whatever is the have a smaller distance, then is the better. That is the best solution. Is a better solution. But I can choose different combinations. What if next time I choose 6 and 5 as seeds? Then I will have another distance. What if I choose 2 and 3 as seeds? Then I will have another total distance. Essentially, I will have a lot of combinations. What is the best? One of them should be the optimum. So we will try to calculate, in this case, how do we arrive to the best solution. The best solution will be try all the possibilities and choose the one with the smaller distance. How do we calculate distance if we are given this matrix? What is the distance or the similarity between 1 and 2? 1, you can think in 1 as these are rows of 1s and 0s. Here the empty spaces are zeros. 2 is characterized by this vector of 1s and 0s. So we calculate the distance with this formula. Summation of absolute value of aik minus ajk. Aik is essentially the number 1 or 0 in the position I, column k, minus 1s or zeros of j, column k. Summation of that after you take the absolute value. It's going to be clear if I show you one example. How do we calculate the distance between machine 1 and 2? 1 is this, 2 is this. Formula says 1 minus 0, 1. 0 minus 1, minus 1. Absolute value, 1. I got 2. No. 3, 4, no. 5, 6. That's why distance between 1 and 2 is 6 based on this formula. What about distance between 1 and 3? Between 1 and 3, 1 column, third column. No. 1, 1. 1 and 3, 1. Okay? Then you can fulfill this matrix. What is the distance between 1 and 1? The distance is 0, because essentially the machine will not travel back. Okay? Given this distance matrix, at this point we are going to explain the formulation of the p-median procedure. Later we will implement in Excel for this example and this distance matrix. Okay, so let's explain the formulation of the p-median problem. As always, in these optimization problems you have 3 parts. First part is the decision variables. What are the decision variables that we are going to declare? Our first decision variable is going to be xjj, which is going to take a value of 1 if point j is a seed point, or 0 in any other case, 0 otherwise. So here in this case j goes from 1 to 6. Here I have 6 variables. Next decision variable, xij equal to 1 if a non-seed point I is assigned to a seed point j, 0 otherwise. In our case, I goes from 1 to 6 and j goes from 1 to 6. That's why xij, essentially here I have 36 decision variables for our small example of 6 machines. That is the first part of the formulation. What is the second part? The objective function. You usually, in these optimization problems, you want to minimize or maximize something. In this case, we want to minimize the distance that machines travel. How do we essentially state the objective function? With this formula: dij times xij summation over j summation over I. This formula will give you essentially the distance that machines will travel. Remember, xij are decision variables, xij, and also xjj takes a value of 1 or 0. It means that these decision variables are binary, just 1 or 0. So here this will have a value of 1 or 0. It depends. So sometimes the contribution is going to be annihilated, eliminated, based on that xij could be 0. What about the constraints? We cannot choose essentially decision variable freely. We have some constraints. What are the constraints? First constraint: summation of xij equal to p, where p is the number of groups or the number of seeds that I want. If I have 2 seeds, at the end of the procedure I will have 2 groups. If I have 3 seeds, at the end of the procedure I will have 3 groups. That's why I'm essentially calling number of seeds or number of points or number of groups the same. So summation of xij should not exceed p, should be actually equal to p. Next restriction. The next restriction is summation of xij equal to 1 summation over j for every I. Every point I has to be assigned to just one group. So this constraint assures or guarantee that each one of the points or machines is going to be assigned to just one group. We don't want to assign our machine to 2 groups. That doesn't have sense. It should be assigned to just one group. Okay. Next constraint. Here, how many constraints do I have here? Here in the first one I have 1 constraint. Here I have, if I goes from 1 to 6, I will have 6 constraints. Okay. Next constraint: xij less than or equal to xjj for every ij. This constraint, these set of constraints, essentially guarantee that every point is going to be assigned to a seed point. Each machine needs to be assigned to a seed point. It cannot be assigned to a non-seed point. That is not possible. Okay. Maybe this will be clear later when we implement this procedure on Excel. So in this sheet I am going to do that. I am going to essentially have my decision variables here. Decision variables. So these cells that I have highlighted with this orange color, these cells from 1 to 36 in this case will be my decisions variables. They can have values of 0 or 1, just 0 or 1, 1 or 0. Remember, then you can complete all these lines. These are binary variables. You cannot have a 3 or something different than 0 or 1. Just to label this, let me label with x11, x12, and this up to x16. Then I will have x21, x22, and then up to x26. The same for 3, x31, x32, x32, x33, up to x36. So let me pause the video while I complete this. Okay, I have completed all the labeling of this decision variable. Just to reference, the actual cells that are going to be part of the formulation are these orange ones. These are just some labeling that I will use to reference. So what about the objective function? I will calculate the objective function in this yellow position, and contribution of each one of the decision variables I will enter in this location, in this light yellow location. So I can essentially identify this with contribution. So what will be the contribution or the distance if machine 1 travels to machine 1? 0. What will be the distance if machine 1 travels to machine 2? 1 to 2, 6. 6. 1 to 3, 1 to 3, 1. 1. And let me pause the video while I complete all of this. Yeah, I have completed the contribution. So if I want to calculate the total distance that machines will travel once I identify the cells, and once each one of the machine is assigned to the cells or the seats, and the formula would be something like this. This is equal to this times this plus x12 times the contribution plus x13 times the contribution. Remember, we have that in our formulation of an objective function. Distance times variable times distance. Plus this times this let me repeat, I have some problems with this formula. Plus this times this plus decision variable times contribution plus decision variable times contribution plus decision variable times contribution So I should stop the video, I should pause the video while I complete this. So finally I have completed all of the calculation of this objective function. So this moment is 14 because I enter some ones here. Maybe if all of them are 0, I don't know. At the beginning, if all of these decision variables is 0, what is the objective function? 0. If I enter some ones like here, maybe here, then you can see how my objective function essentially changed, because I have some ones inside these decision variables. Okay, so the contribution, if I put a 1 here, then it's going to contribute with 3. Instead of 21, it's going to be 24. Okay, so we have essentially the objective function, we have the decision variables, but we cannot enter any value of the decision variable. We are not allowed to do that. If somebody wants to minimize this, if somebody wants to minimize this objective function, what will be a good option? To put 0, in all the decision variables, and you have minimized your objective function. Is 0. Is that possible? No, because we have some restrictions. What are restrictions? So let's try to enter the restrictions here. What are the restrictions or constraints? What's the first constraint? Summation of xij is equal to p. So how many groups do we want? Summation of xij equal p. So here maybe I can calculate the summation of xjj. It is equal to this, you have one xjj plus this, you have another xjj plus 3 plus 4 plus 5 plus 6 then you have the summation of xjj. Summation of xjj need to be equal to how much? Equal to p, remember? So what is the value over p? Let's say that I want p equal to 2. Okay, so summation of xjj is going to be equal to 2. So here I have my first constraint in this cell. Let me use a different color here. So here I have my first constraint. I have one constraint from this. Another constraint, summation of xij equal to 1 for every I. So I will have 6 constraints. One for I equal to 1, another one for I equal to 2, another one for 3, and so on until 6. Summation of xij. So for I equal to 1, I need to add x1 2, okay, plus x1 3 plus x1 4. Okay, so here this is going to be equal to x, let me think, for I equal to 1 1 1 1 2 1 3 1 4. Okay, so in this cell I'm going to store the summation of x11 plus x12 plus x13 plus x14 plus x15 plus x16. Okay, according with my constraint, this should be equal to 1. So let me just enter this. This should be equal to 1, just to remember. Same for the rest. So I can do this. This is equal as sum of this. This is for I equal to 1. This is for I equal to 2. Next one. This is for I equal to 3. This is for I equal to 4. This is for I equal to 5. This is for I equal to 6. This is better. All of them should be equal to 1. Why? Because essentially every point needs to be assigned to just one group. This constraint prevents us from assigning to more than one group. Okay. Here I have my 6 constraints. Maybe I can use a different color just to recognize these constraints. Next constraints. Xij less than or equal to xjj. So we have a lot of constraints here. Xij. So for I equal to 1, how do I expand this? 1, 1 less than or equal to x1, 1. 1, 2 less than or equal to x2, 2. 1, 3. 1, 1. Less than or equal to x1, 1. x1, 2 is going to be less than or equal to x2, 2. Let me just label this so I can easily remember. x1, 3 is going to be less than or equal to x3, 3. x1, 4 is going to be less than or equal to x4. x1, 5 is going to be less than or equal to x5, 5. And up to x1, 6 is going to be less than or equal to x6, 6. So I need to do this. x1, 1. This should be less than or equal to x1, 1. So here is also x1, 1. x1, 2 here should be less than or equal to x2 is it here. x1, 3 should be less than or equal to x3, 3. x1, 4 should be less than or equal to this cell x4, 4. x1, 5 should be less than or equal to x5, 5. Where do I have x5, 5? x1, 6 should be less than or equal to x6, 6 here. Okay, all of this is just for I equal to 1. So all of this is less than or equal to. Let me use this symbol. Less than or equal to. So this is just for I equal to 1. For I equal to 1, I have 6 constraints. For I equal to 2, I will have another 6 constraints. This constraint is going to be x to 1, sorry, x to 1, x to 2, x to 3, and up to x to 6. Here this is going to be less than x, as the same as here. Okay, so let me pause the video while I complete this. So I will have another 6 for 2, another 6, so I will have 36 more constraints. Let me pause the video. So here I have completed all the constraints. 6 for I equal to 1, 6 for I equal to 2, another 6 for I equal to 3, 4, 5, and 6. All of them should be less than or equal to xjj, is this constraint, the one that assures that a point is assigned to a seed. Because let's say that 1 is a seed point. If this is 1, okay, maybe another point could be x4 for 1. It means that the rest of them are 0. So you cannot have x12 equal to 1 because you have a 0 in front of it. Okay, so you are not going to assign 1 to 2. Okay. Similar in the second group, if x1 is 1 and x44 is 1, it means that x22 and x33 and x55 are 0. Why? Because the first constraint assures that you will have just 2 seeds. So if this is 0, if x2 is 0, you cannot have a 1 here. It should be less than or equal to. Okay? So right now you can see how if I change these values, right now all of them are 0. My objective function is 0. If I start entering some values here like 1, 1, then my objective function changes, and also wherever I enter a 1, also it's copied here. For instance, let's say that x35 is 1. You will see how this cell will change. x35 is 1. Okay? So right now we are ready to start changing values here. Changing values. I want a computer to change value here. Trying to minimize this yellow function. But the computer should not violate these restrictions. For instance, let's say right now I enter some ones here. You see how this restriction is not fulfilled. Okay, I do not have the summation of x11 plus x22 plus x33 x44 up to x66 is not 2. Okay, so probably I can, if I put a 1 here and a 1 here, then I have a 2. But probably I am violating another constraint. Look at this. This should be equal to 1. Right now is equal to 3. This should be equal to 1. Right now is 2. So what are the values that I need to put here without violating these constraints that minimizes this number? So I want a robot to start changing, a robot or computer, whatever, to start changing these numbers until he arrived to a solution that essentially fulfill these constraints, minimizing this objective function. How can I do that? I can use the solver in Excel. The solver will do that job for me. So let's start from 0, all of them 0, 0, the objective function. So I will select data solver. If you have not installed this plugin, it is easy to install. solver. First, what is your objective function? Select your objective function. Is this? What do we want to do? Maximize, minimize, minimize. Changing what cells? What are your variables? I want you machines to change these cells. Please change those cells for me. What are your restrictions? Let me select my restrictions. I want this cell to be equal to this cell. First restriction. Second restriction, this cell equal to this cell equal. Actually, I can select all this column. I want equal to all this column. So right now I have 7 restrictions. I have another restrictions here, 36 more, all of them less than or equal to. Because all of them are less than or equal to, I can select all of them at once. All of these less than or equal to all of this. Okay. Do I need another restriction? Yes, one more restriction. These numbers here, my decision variable, cannot be whatever number. Cannot be 10, cannot be negative. They should be binary, just 1 or 0. So that is another restriction. Please computer, these decision variables are binary. So do not enter any number different than 1 and 0. So we have finished. Okay, we have our objective function, we have our decision variables, we have our restriction. One of the restriction is a binary. So let's run this simulation and try to see if we arrive to a solution. Cross fingers. Okay, then I have one solution. Let's accept the solution that solver gives me. The solution that solver gives me say x11 equal to 1, 251, 311, 1, 551, 651. Okay, so 1 and 5 are my seed points. 2 is assigned to 5, 3 is assigned to 1, 4 is assigned to 1, 5 is assigned to 5 because it's a seed point, 6 is assigned to 5 with a total distance of 8. So my solution for p equal to 2 is x. Actually I have the solution here. For p equal to 2 is x11 equal to x31 equal to x41 equal to x55 equal to x25 equal to x65 equal to 1 with a total distance travel of 8. So I have 36 variables, binary variables. I have 43 constraints, 1, 6, total 7 plus 36, 42. And this is my solution for p equal to 2. What if I change the number of seeds? So let's change this number to 3 and rerun the simulation. So let's call again solver here in the data tab, solver. I do not need to enter again the cells, all of them are already there, so I just need to run again. Okay, I have another solution, this time for p equal to 3. For p equal to 3, you can see how x11 is a seed, 2 to 5, 3 to 1 not a seed, 4 to 1 no a seed, 5 5 a seed, and 6 6 a seed. Your solution for p equal to 3 is x11, x31, x41, x22, x52, x66 equal to 1 with a total distance of 5. Okay? Hopefully this video will help you.